A warming Midwest increases likelihood that farmers will need to irrigate if current climate and crop improvement trends continue into the future. Midwestern corn growers who today rely on rainfall to water their crops will need to irrigate their fields, a new study finds. This could draw down aquifers, disrupt streams and rivers, and set up conflicts between agricultural and other human and ecological needs for water, scientists say. The study, reported in the journal Ecosphere, calculated the extent to which hotter conditions expected by mid-century will draw more moisture out of corn plants, said University of Illinois plant biology professor Evan DeLucia, who led the study. As the atmosphere warms, it dries, and so the draw for water to go from plants to the atmosphere increases, DeLucia said. The ability of the atmosphere to draw water from plants is determined by its vapor pressure deficit. If you add to this the decades-old trend toward bigger, more productive corn plants, you see an overall increase in water use and water loss through plant leaves, without comparable increases in rainfall to counter the deficit, he said. Today, average corn yields across the Midwest are roughly 170 bushels per acre, DeLucia said. This is up from about 120 bushels per acre in 1990. If this trend continues, the projected yield in 2050 would be 230 to 240 bushels per acre averaged across the Midwest, he said. If you want more corn, then you have to have a bigger plant, and a bigger plant is going to use more water. Precipitation is not expected to increase enough in the Midwest to compensate for the drying conditions of the warmer atmosphere, the researchers found. We are getting more intense storms in the spring and less rain in the late summer, DeLucia said. But the overall amount of precipitation is not expected to change much in the coming decades. Even without increases in plant size and productivity, warming conditions alone will necessitate a much greater demand for water, the team found. We show that as vapor pressure deficit increases, maintaining current maize yields will require a large expansion of irrigation, greater than threefold, in areas currently supported by rain, the researchers wrote. Some strategies can help counter the drying conditions, DeLucia said. The use of minimum tillage and mulches can reduce the rate of water loss from the soil. And breeding or genetically modifying plants to sequester more chlorophyll in their lower leaves and less in the top will allow photosynthesis to proceed more efficiently closer to the ground, where conditions are more humid. This will lessen the amount of moisture lost when plants open the pores in their leaves to take in carbon dioxide during photosynthesis. A research effort to do this is underway in the laboratory of U of I plant biology professor Donald Ort. Controlling temperatures for inexpensive plant experiments. A study out of Clemson University has demonstrated that inexpensive, easy-to-use temperature controllers are able to provide reliable set temperatures for the detailed observation of developmental rates in response to different temperature treatments. Researchers Douglas Bielenberg and Ksenia Gasic engaged a methodical examination of the practical applications of these temperature control devices on cut stems, buds, and seeds. The results of their study are detailed in the article, Controlled Temperature Treatments with Low-Cost Off-the-Shelf Equipment for Bud or Seed Forcing Experiments, published in HortScience. Inexpensive plug-and-play temperature controllers have recently become available. These allow a chest freezer to be programmed easily to hold a desired set point across a range of biologically relevant temperatures. Installation can be completed in a few minutes using consumer-grade chest freezers. Characterizing the regulation of plant and seed development by temperature requires controlled exposure of replicate plants, whole or in part, to multiple temperature environments simultaneously. Experiments with seeds or other small plant segments can be performed on a thermal gradient table, which can generate many temperatures at once. However, experiments involving larger plant parts, such as cut stems, require temperature control of a larger three-dimensional volume, such as an environmental chamber. Inexpensive access to the number of environmental chambers required for this sort of scientific observation is not easily available and can therefore limit the scope of experiments. However, newly available plug-and-play temperature controllers allow conversion of a standard chest freezer into a controlled environment chamber in minutes, with no custom modification. To test the equipment, the researchers subjected an array of identical plant types and seeds to a variety of precise temperatures within an array of identical box freezers, chambers. They tested each chamber's temperature controller, recording internal temperatures at 10-minute intervals, to ensure the integrity of the equipment and the consistency of its output to maintain an exact and controlled environment during a 48-hour period, during which the chambers were not opened. The effectiveness of the chambers on the effects of temperature on developmental rates was assessed with 2 biological assays: bud break progress of peach floral buds warm forced at different temperatures, and sunflower seed germination. Both bud break and germination showed a clear temperature-dependent effect on development, with each decrease in temperature slowing development from the previous temperatures. Understanding the minimum temperature for development is an important realm of knowledge for modeling plant phenology. The relationship between development rate and suboptimal temperatures can be used easily to calculate an estimated base temperature for optimal growth. These newer inexpensive temperature controllers will allow horticulturists, agronomists, foresters, and educators to design and perform experiments when multiple controlled temperature environments are required without access to specialized facilities or skills. Off-the-shelf, easy-to-use components offer the potential to expand greatly the community of researchers who are able to incorporate temperature physiology into their investigations of plant development and phenology, particularly workers outside of traditional research institutions.